We always see the same face of the moon, but what secrets hide on the far side forever turned away from Earth? Scientists have discovered surprising clues, and the mystery is deeper than most imagine. Stay with us as we explore what's hidden in the dark side of the moon. If you enjoy this journey, please like, subscribe, share, and tell us in the comments what you think might be out there. Thank you for watching. Now let's begin. The phrase dark side of the moon suggests a hidden hemisphere that never sees sunlight, yet the reality is quieter and more ordinary. The moon presents one face toward Earth because its rotation period matches its orbital period. This state is called synchronous rotation. One hemisphere always faces Earth and is called the near side. The opposite hemisphere faces away from Earth and is called the far side. Both hemispheres move through the same cycle of day and night under the sun. The far side is not permanently dark. It receives sunlight for long stretches and then spends an equal length of time in night, just as the near side does. What changes is not the light from the sun, but the view toward Earth. On the near side, Earth hangs in the sky and shows phases. On the far side, Earth never rises. The sky remains free of that large blue and white disk. The term far side is therefore precise and avoids confusion. Synchronous rotation sets the rhythm that makes the far side seem mysterious from an earthly viewpoint. The moon spins once on its axis during each trip around Earth. Because these two motions take the same amount of time, the same hemisphere stays turned toward Earth. A person standing near the lunar equator on the near side watches Earth almost fixed in the sky, slowly changing phase while the sun climbs arcs and sets over a very long lunar day. A person standing in a similar spot on the far side experiences the same slow sunrise, the same long noon, and the same lingering dusk, but there is no Earth in the sky. Stars spread across the black dome, and the sun alone provides daylight. The length of the lunar day is much longer than a day on Earth. With no atmosphere to scatter sunlight, the boundary between day and night on the surface called the terminator is sharp. As the terminator moves across the far side, sunlight pours across crater rims and highlands with a slow, steady advance. Shadows extend for long distances in the low sun of early morning, then shorten near midday, then lengthen again as evening approaches. This slow cycle does not hurry. It progresses at a measured pace set by the moon's orbit. The far side therefore spends long periods in bright sunlight and long periods in night, but never remains dark forever. The phrase dark side can be set aside in favor of clearer language. The far side is simply the hemisphere that faces away from Earth. It holds the same kinds of landforms as the near side, including craters, mountains and plains, and it undergoes the same daily change in lighting. The difference is in what can be seen from Earth. Because the far side is turned away, it is hidden from ground-based viewing. For many years, its landscape remains unknown from a human standpoint, which encourages the idea of darkness as absence of knowledge rather than absence of sunlight. When sunlight falls on the far side, it strikes rock and dust that reflect light differently from the smoother lava plains that dominate parts of the near side. The far side is dominated by bright highlands that appear pale under the sun. These highlands stand out in the crisp shadows of low sun angles. The light has no haze and no colour shift from air, so contrasts are strong. Crater walls cast sharp edges. The floors of small depressions remain in shadow until the sun climbs high enough to clear their rims. At local noon, the light is intense and unfiltered, and the surface appears harsh and detailed. At local sunset, the same ground cools quickly, and the shadows return with long blue-black tones against sunlit ridges. All of this happens without the presence of Earth in the sky to provide faint reflected light. On the near side during night, Earth can act as a secondary source of light called earthshine that gives a dim glow to the landscape. On the far side there is no earth shine. Night becomes very dark. Starlight and the faint glow of the zodiacal light are the only illuminations. The cycle repeats with each long lunar day. The constancy of this pattern helps explain how a simple mechanical relationship gives rise to a persistent misunderstanding. People see the same face of the moon from Earth, and naturally think the other face must be dark. A clear description corrects this synchronous rotation, fixes one hemisphere toward Earth, not toward the Sun. The Sun still rises and sets on both sides. This understanding also clarifies the phases of the Moon. The phase depends on the geometry among the Sun, Earth and the Moon. When the near side looks full from Earth, the far side is in midnight under a dark sky. When the near side looks new from Earth, the far side sits in broad noon under the Sun. Each quarter and crescent is matched by a complementary lighting pattern on the far side. The far side's day is the near side's night, and the far side's night is the near side's day, apart from small shifts due to the subtle wobble called libration. The main idea remains that both hemispheres share sunlight over time. The quiet precision of the terms near side and far side keeps the focus on geometry rather than on mystique. The far side is hidden from direct earthly view but not hidden from the sun. It does not hold a different kind of day. It holds the same slow progression of illumination that every point on the moon experiences, the absence of an atmosphere, the long duration of daylight and darkness, and the lack of earthshine combine to give the far side its particular visual character. Craters appear stark, ridges emerge cleanly. The sky during day is black even when the sun is high. During night it is deep and clear. This scene unfolds at a pace that supports careful looking and careful thinking. By setting the terms accurately at the start, the mind can move through the far side without assumptions. The far side is not dark. It is simply the moon seen from the other side of its partnership, with Earth turning once per orbit, keeping its face oriented by a balance of motions and sharing sunlight with the near side in long, even steps. Tidal locking is the quiet outcome of a long exchange between gravity shape and internal friction. The moon begins with a rotation that does not match its orbital period. Gravity from Earth pulls more strongly on the near side of the moon than on the far side. This difference across the body is called a tidal force. It stretches the moon slightly along the line toward Earth and compresses it across that line. Even solid rock responds not as a liquid wave but as a slow elastic rise and fall called a solid tide. The height is small, yet the effect matters because the rise and fall are not perfectly in step with the pull. Inside the moon, minerals flex, slide and rub at grain boundaries. A little energy is lost as heat each cycle. That loss is called dissipation. Dissipation is the key that turns a steady gravitational tug into a brake on rotation. If the moon spins faster than it orbits, the tide raised on its surface is carried a little ahead of the direct line to Earth. The bulge leads because the material has internal friction and cannot react instantly. Earth's gravity then pulls backward on that lead, exerting a torque that slows the spin. If the moon spins more slowly than it orbits, the bulge trails the line to Earth. Gravity then pulls it forward, exerting a torque that speeds the spin. There is one special rate at which the bulge neither leads nor trails on average. That rate is one spin for one orbit. It is a 1-to-1 spin-orbit resonance. At that point, the torque that changes the spin tends towards zero, and small deviations are corrected. Faster spin is braked. Slower spin is nudged forward. The result is a stable balance. The moon settles into synchronous rotation. The alignment is not perfect at every moment, because the orbit is a slightly stretched oval rather than a perfect circle. The direction toward Earth varies in speed along that oval, and the moon's body responds with a small periodic wobble called libration. Over time, the average remains one turn per orbit. The mechanism does not require an ocean. Rock alone is sufficient because even hard minerals deform a tiny amount under stress. The amount of lag between the tidal pull and the body's response depends on temperature composition and structure. A warmer, softer interior dissipates more energy each cycle and locks more quickly. A cooler, stiffer interior dissipates less and locks more slowly. The thickness of the crust, the depth of the mantle, and the presence of partial melt at any time in the past all change the pace. Scientists describe this with a measure called a tidal quality factor, which tells how many cycles occur before energy decays significantly, and with a measure of how much the body deforms called a love number. The exact terms are not needed here. The idea is simple. Greater dissipation means faster capture into the stable state. Lesser dissipation means slower capture. In the early history of the Moon, when the interior holds more heat, dissipation is stronger, and the path to locking is shorter. As the Moon cools, the process slows, but by then the spin has already approached the stable rate. Once synchronous rotation is established, it is hard to disturb. The same tidal forces that brought the Moon to the balanced state work to restore it, if something nudges the spin away. A big impact can shift the figure slightly. A slow change in the orbit can alter the exact timing along the path. The locked condition holds because the torque always acts to align the tidal bulge with Earth on average. The bulge itself is not only the temporary rise and fall of solid tide, it also becomes partly frozen into the permanent shape of the Moon, which is slightly elongated along the Earth line. This permanent figure creates a gravitational handle that keeps the same hemisphere oriented toward Earth. The story does not end at the Moon. The same tidal forces act on Earth. The Moon raises ocean tides and smaller solid tides in Earth's rock. Because Earth spins faster than the Moon orbits, the tidal bulge on Earth is carried ahead of the line to the Moon. Gravity then pulls back on that bulge, slowing Earth's rotation by a tiny amount, and pushing the Moon outward a tiny amount by transferring angular momentum to its orbit. The rate is small, only a few centimeters of outward drift each year, but the effect adds up across deep time. This outward drift changes the orbital period slightly and keeps the synchronized state in step. The coupling between Earth and the Moon therefore sets both the pace of Earth's day and the details of the lunar orbit in a slow linked evolution. None of this requires any special intent or hidden agency. It is a mechanical result of differential gravity-material response and the conservation of angular momentum. The energy lost from the Moon's early faster rotation appears as heat inside the body and then radiates away into space. The angular momentum taken from the spin appears as a change in the orbit. Each cycle of tide and lag and torque is tiny. The accumulation over millions and billions of cycles is large. The same logic explains why many large moons around giant planets also show synchronous rotation. Some bodies with more elongated orbits can settle into different resonances, such as 3 spins for every 2 orbits, when the torques balance at another ratio. The Moon's nearly circular path favours the 1-to-1 case. The simplicity of the lunar result is helpful for understanding the surface experience described earlier. Because the Moon keeps one face directed toward Earth, the pattern of illumination across its surface is governed by the relative positions of Sun and Earth along the orbit, not by any rapid twist of the body itself. Daylight on the far side follows the long lunar day. Night on the far side follows the long lunar night. The boundary between them moves at a steady pace set by orbital motion. Synchronous rotation fixes the relation between the ground and the sky so that Earth remains fixed above the near side and absent above the far side, while the Sun rises and sets everywhere over the same long cycle. The cause is not a permanent absence of sunlight on one hemisphere. The cause is the stable alignment produced by tides, friction, and time. The more carefully each term is set, the more easily the mind follows the chain from a small difference in gravitational pull. to a small delay in a material response to a steady torque, to a simple and lasting rhythm. The Moon reaches the balance and keeps it turning once each time it circles Earth. This is tidal locking in plain view. The far side of the Moon is not simply a duplicate of the near side with Earth hidden behind its horizon. High-resolution mapping from orbit reveals that the two hemispheres are strikingly different in their surface appearance, crustal thickness and volcanic history. This global asymmetry is one of the most important discoveries in lunar science. It explains why the far side remained enigmatic even after the first spacecraft images, and why scientists continue to examine it closely today. When one looks at the near side, broad dark patches stand out to the naked eye. These patches are called Maria from the Latin word for seas, because early astronomers mistook them for oceans. They are vast plains of basalt formed when lava flooded low areas billions of years ago. They cover nearly 1/3 of the near side. Between the Maria lie lighter highlands made of older crustal rocks. The far side presents a very different picture. It is almost entirely highlands, pale and rugged, with only a few scattered dark plains. The contrast is sharp. Where the near side shows broad, smooth areas that one can trace across hundreds of kilometers, the far side shows dense cratering and mountainous terrain with only small pockets of volcanic fill. Remote sensing confirms that the crust on the far side is thicker than on the near side. The thickness difference is on the order of tens of kilometers. This extra thickness made it harder for magma from the mantle to reach the surface on the far side. As a result, basalt flooding was far more limited there. The result is the greater symmetry in the distribution of Maria. This finding changes the basic view of the Moon. It is not a simple sphere of uniform layers. It is a body with a lopsided internal structure, probably linked to its early thermal and orbital history. Scientists have proposed several models to explain the difference. One possibility is that when the Moon first formed from debris after a giant impact, its orbit was closer to Earth, and one side remained hotter because Earth still radiated intense heat. That difference could have influenced how the crust solidified. The side facing Earth may have cooled more slowly, remaining thinner, and holding more heat-producing elements, while the far side cooled more quickly, creating a thicker crust that became less volcanically active. Another possibility is that large impacts redistributed heat-producing elements unevenly, or stirred the crust and mantle in ways that left lasting contrasts. What is clear is that the asymmetry is not just a surface feature. Gravity data from spacecraft show that the distribution of mass beneath the crust also differs between hemispheres. The near side contains regions called mass concentrations or mascons beneath large basins. These mascons are dense materials that pull more strongly on passing spacecraft, altering their orbits. The far side has fewer such concentrations. Instead, it shows thicker crust and fewer deep flooded basins. This difference is visible not only in orbital data, but also in the pattern of craters. On the far side, craters remain more intact because they were not erased or filled by lava flows. On the near side, many craters are buried or partly buried by the basalts of the Maria. When spacecraft such as Lunar Orbiter and later Lunar Reconnaissance Orbiter mapped the surface, the sharp contrast stood out in detail. The far side became known as the heavily cratered face, while the near side became known as the face of Maria and Highlands together. This dual character makes the Moon unique among large rocky bodies in the inner solar system. Mars and Mercury show volcanic plains spread across their surfaces without a clear near versus far side difference. Earth itself is far larger and undergoes plate tectonics which erases such earlier symmetries. The Moon preserves its record more clearly. The far side's ruggedness is not only a visual impression, but also a record of billions of years of impacts preserved without much resurfacing. Because no large maria formed to cover it, the far side retains older terrain that can be sampled to learn about the earliest periods of lunar history. Samples from the Apollo missions all come from the near side because spacecraft had to remain in radio contact with Earth. They show a mix of basalt from the maria and anorthosite from the highlands. Samples from the far side are rare, collected only by a few robotic missions. These confirm that its crust is dominated by anorthosite, which is a rock made mostly of the mineral feldspar formed from the floating upper layers of a global magma ocean early in the Moon's history. This adds more weight to the idea that the far side preserves a thicker, less altered shell of that early crust. The visual asymmetry that strikes the eye is thus rooted in deep processes. A person standing on the near side and a person standing on the far side would both see sun and stars, but the landscapes would differ greatly. The near side observer might walk across wide basalt plains with few craters, while the far side observer would cross rough highlands, filled with overlapping craters of many sizes and with very little open plain. The difference has implications beyond geology. Because the far side has no maria dominating its appearance, it is dominated by lighter highland rocks. These reflect more sunlight. The albedo or reflectivity of the far side is higher. Spacecraft photography measures this directly. The near side averages darker shades because basalt is dark, while the far side averages brighter shades because anorthosite is pale. To the human eye on the surface, this means the ground of the far side would look brighter under the same sun angle. The contrast of light and shadow would be sharper, while the dark maria of the near side would absorb more light and give a darker cast. The far side and near side, therefore, are not interchangeable. Each holds distinct information about how the Moon cooled, how it was bombarded, and how its interior evolved. The asymmetry continues into the interior as well. Seismic data from the Apollo missions combined with gravity data from modern orbiters suggest that the distribution of dense materials, lighter crust and heat-producing elements is not uniform. The far side is poorer in the combination of potassium rare earth elements and phosphorus known collectively as carip, which play a role in maintaining heat and fueling volcanism. The near side is richer in these materials, which may explain why it experienced more extended volcanism. The far side, with its thicker crust and lower internal heat, remained quieter after the first few 100 million years. The scientific focus on asymmetry is not dramatic but steady. Step by step, the mapping of each hemisphere reveals how simple terms like far side and near side cover much deeper differences. This sets the stage for further questions about the far side's unique regions such as the Great South Pole Aitken Basin and the distribution of elements across the crust. These questions continue to guide exploration. For now, the main point is clear. The Moon is not a body of two identical halves. It is a body with one face dominated by basalt plains and mascons, and another face dominated by rugged highlands and thicker crust. This quiet but striking asymmetry is written across its entire surface and under its crust. When spacecraft first photographed the far side of the Moon, scientists immediately noticed that it was dominated by pale highlands. These bright, rugged regions cover most of that hemisphere, and their composition provides a direct window into the earlier stages of lunar history. The rocks that make up the far side highlands are primarily anorthosite, which is a type of igneous rock rich in the mineral plagioclase feldspar. This mineral forms when lighter components in molten rock rise and solidify near the surface. The story of these rocks begins with the idea of a lunar magma ocean. Shortly after the Moon formed from the debris of a giant impact, its surface and much of its interior remained molten. Heat from the collision itself, from the decay of radioactive isotopes and from continuing impacts kept the body at high temperature. In this molten state, heavier minerals such as olivine and pyroxene tended to sink toward the interior, while lighter feldspar crystals floated toward the top. Over time, these floating crystals formed a thick, buoyant crust made of anorthosite. This crust is preserved today as the feldspathic highlands that dominate the far side. The evidence for this story comes from both rock samples and remote sensing. Apollo missions collected samples of anorthosite from the near-side highlands, and later robotic missions brought back material from the far side. Laboratory analysis shows that these rocks are composed of more than 90% plagioclase, with ages dating back over 4 billion years. These ages make them some of the oldest solid surfaces in the solar system. Spectrometers on orbiting spacecraft confirm that similar compositions extend across the far side, particularly in regions where the surface is not covered by younger ejecta from impacts. The texture of these rocks is coarse, showing that they crystallize slowly in a magma body rather than forming rapidly at the surface. The abundance of anorthosite suggests that the entire Moon once had a global molten layer. The highlands crust is the frozen top of that ancient ocean. The far side's dominance by this type of crust means that it preserves a clearer record of those earliest times than the near side, where many regions have been resurfaced by later volcanism. This surface appearance of the highlands reflects their composition and their age. Anorthosite is relatively light in colour, so under sunlight the highlands appear bright compared with the dark basalts of the Maria. Because these regions have been exposed for billions of years, they are heavily cratered. Each new impact digs into older material, scattering fragments across the surface. The result is a dense record of overlapping craters of every size, from tiny pits to enormous basins. On the far side, where lava flooding did not erase these features, the cratering record is nearly continuous. To walk across such terrain would be to step over countless small ridges and depressions, all products of ancient impacts preserved without later burial. The crust beneath the far side highlands is also thicker than on the near side. Measurements from gravity mapping show that in many places the crust reaches 70 kilometers in thickness, compared with 30 or 40 kilometers on the near side. This greater thickness may have made it more difficult for magma to erupt, which explains why the far side has fewer volcanic plains. Instead, its surface has remained largely as it was after the initial solidification of the magma ocean, modified mainly by impacts. This makes the far side a natural laboratory for studying the primary crust of the Moon. The feldspathic composition also influences the way the surface responds to space weathering. Constant bombardment by micrometeorites and solar wind particles gradually darkens and alters the outermost grains. Yet the underlying composition remains clear in spectral data. The prevalence of Pleioclase feldspar creates a diagnostic absorption feature in reflected light, which instruments on orbiters can detect. By mapping this feature, scientists can trace the extent of the feldspathic crust and distinguish it from the basaltic regions where lava once flowed. The global distribution confirms the asymmetry. The near side shows large basalt provinces surrounded by highlands, while the far side is almost entirely feldspathic highlands, with only a few isolated basaltic deposits. The feldspathic highlands are not uniform. Some regions have thicker crusts, some thinner. Some show large basins where impacts excavated deeper materials. The South Pole Aitken Basin, which will be discussed later, is one example where the impact penetrated through the anorthosite layer and exposed underlying rocks. Elsewhere, smaller basins scatter debris across the highlands, mixing different layers. Despite this variety, the overall picture is one of continuity. The far side is dominated by the remains of the floating crust that solidified out of a global melt in the earliest days of the Moon. This interpretation fits with broader ideas about planetary formation. Other large bodies such as Earth, Mars, and Mercury likely experience similar magma ocean stages. On Earth later, tectonics and recycling destroyed that record. On the Moon, the absence of plate tectonics preserved it. The far side, shielded from extensive volcanism, preserves it most clearly of all. Scientists continue to test details of the magma-ocean hypothesis. They study isotopic ratios in feldspar to determine crystallization histories. They model the cooling of a global melt to see how long it would take and what minerals would form at each stage. They compare the distribution of feldspathic highlands to predictions from these models. Some questions remain open, such as how deep the magma ocean was, whether it extended to the core, and how completely it mixed. But the broad outline is widely accepted: the far side highlands are the frozen float of a once molten moon. From a descriptive standpoint, the far side highlands present a rugged and unyielding landscape. Peaks rise steeply, their slopes fractured by billions of years of impacts. Valleys lie in shadow until the slow movement of the Terminator brings them into light. The surface is uneven, strewn with ejecta blocks and coated with fine regolith, created by continual micrometeorite bombardment. The brightness of the rock under direct sunlight contrasts with the stark black of the sky, emphasizing the absence of atmosphere. For a human observer, the impression would be of brilliance and harshness, yet stillness. Nothing stirs the dust except new impacts, and those occur rarely on human timescales. In this way, the Farside Highlands combine physical evidence and visual effect. They are both a geologic record and a striking landscape embodying the story of the Moon's early solidification. To understand them is to understand why one hemisphere appears so different from the other. The Feldspathic Highlands define the far side and provide the strongest evidence that the Moon once held a molten ocean whose lighter minerals floated to the top. They remain as a lasting testimony to that global transformation, preserved more clearly here than anywhere else on the lunar surface. The scarcity of volcanic plains on the far side of the Moon arises from simple physical constraints. When lava floods the surface to form Maria, molten rock must rise from the mantle, pass through the crust and erupt onto the surface. On the near side, this happens repeatedly, creating wide basalt plains. On the far side, it happens rarely, leaving most of the crust covered by rugged highlands. The chief difference is crustal thickness. Measurements from orbital spacecraft show that the far side crust is much thicker on average than the near side crust. This extra thickness acts as a barrier. Magma rising from the mantle cools and stalls before reaching the surface. Even when impacts create deep basins, the molten rock has difficulty breaking through. The result is a surface where volcanic flooding is limited to small patches rather than spreading broadly. The timing of internal heat also plays a role. Early in lunar history, heat was trapped within the body by radioactive elements and leftover energy from formation. On the near side, concentrations of radioactive isotopes created long-lasting pockets of warmth. These pockets kept magma chambers active for hundreds of millions of years. On the far side, such heat-producing elements were less abundant. Without this internal energy, the mantle cooled and solidified more quickly, reducing the chance of later eruptions. The difference in heat sources helps explain why the far side highlands remained quiet, while the near side experienced widespread basaltic flooding. Scientists call the heat-producing mixture potassium rare earth elements and phosphorus abbreviated together as CREEP. Orbital spectroscopy shows that CREEP materials concentrate mainly on the near side. Their scarcity on the far side means fewer opportunities for magma to persist and erupt. This contrast fits with the larger asymmetry described earlier. The far side is thicker, cooler, and poorer in heat-producing elements, so its volcanic history is brief and subdued. The geological record bears this out. Basalt deposits on the far side are sparse and scattered. They fill only small craters and depressions rather than sweeping across wide basins. Many are buried beneath ejecta, visible only through careful analysis of remote sensing data. These cryptic deposits show that volcanism did occur but never on the scale of the near-side Maria. To visualize this difference, one can compare Mare Imbrium on the near side with any far-side basin. Mare Imbrium stretches for over 1,000 kilometers, a vast smooth plain of dark basalt. On the far side, the largest basins such as South Pole Aitken or Moscovians contain much less basalt. Their floors remain dominated by anorthosite and impact debris, with only isolated dark patches where lava once managed to surface. The rest of the terrain remains pale and rugged. The lack of Maria means that the far side preserves more ancient craters. On the near side, large flows of basalt covered old features, creating broad, smooth expanses with fewer visible scars. On the far side, nearly every crater remains visible, overlapped and intersecting, creating a densely pitted surface. The absence of extensive volcanic resurfacing thus preserves a more complete record of impacts across time. This difference is valuable to scientists who study impact rates and chronology. By comparing the far side's dense crater record with radiometric ages from returned samples, they can calibrate models of solar system bombardment. The far side offers a surface that has not been smoothed over by later lava, giving clearer evidence of early events. The causes of limited volcanism on the far side are therefore well understood in outline but still open in detail. One line of research explores how crustal thickness evolved after the magma ocean solidified. Perhaps the far side crust crystallized earlier became thicker and blocked magma more effectively. Another line of research examines whether giant impacts redistributed heat-producing elements unevenly, concentrating them on the near side and leaving the far side depleted. A third idea looks at orbital dynamics in the early system. If the young Earth radiated heat toward the Moon, it could have slowed the cooling of the near side, leaving the far side cooler and more rigid. Each of these ideas may contribute part of the explanation. None exclude the others. What remains consistent is the outcome. The far side has fewer Maria because it is less favorable for basaltic flooding. The science is descriptive rather than speculative. Measurements of crustal thickness, maps of creep distribution, and counts of volcanic deposits all support the same conclusion. From a descriptive viewpoint, the far side landscape reflects this quiet history. Under sunlight, it shines with the brightness of feldspar highlands. Few dark plains break the continuity. Where they do appear, they are small and isolated, offering sharp contrast against the surrounding terrain. To stand there would be to see patches of dark basalt encircled by pale walls, a reminder that volcanism touched the far side but never transformed it. In contrast, the near-side plains stretch to the horizon, with crater rims rising only distantly. This stark difference between hemispheres gives the Moon its dual character. From Earth, the Maria make patterns that resemble eyes and faces. From the far side, no such patterns appear, only the rugged terrain of ancient crust. The explanation lies in the internal structure of the Moon, where thickness and heat shaped the outcome. The far side is thicker, cooler, and less volcanic. The near side is thinner, warmer, and more volcanic. This simple balance has held for billions of years. Even today, spacecraft confirm that the far side remains dominated by highlands. No hidden seas of lava lie beneath its surface. Only patches of basalt mark ancient eruptions that never spread far. The far side's story is therefore one of restraint. Where the near side opened to repeated floods of magma, the far side held firm. It became a museum of craters, preserving the scars of impacts that span the solar system's history. It became the face of feldspathic highlands, bright under the sun and dark under the stars. The scarcity of Maria is not an absence to be filled, but a record to be read. It is a reminder that planetary bodies are not uniform. Small differences in thickness and composition can shape entire landscapes for billions of years. The far side's quiet surface, nearly free of vast basaltic seas, is one such outcome written across half the Moon for all time. Among the most striking features on the far side of the Moon is the South Pole Aitken Basin, an immense scar that measures roughly 2,500 kilometers across and up to 8 kilometers deep. It is one of the largest known impact structures in the solar system. Its sheer scale makes it an anchor for understanding the far side, and it offers a rare window into the Moon's interior. When an asteroid or comet struck in the earliest chapter of lunar history, the energy released excavated material from deep layers and reshaped the surrounding terrain on a planetary scale. The basin extends from the lunar South Pole northward to the region known as Aitken, covering almost a quarter of the far side surface. Its outer rim is worn and subdued by later impacts, yet its overall outline remains clear in topographic maps generated by laser altimeters on orbiting spacecraft. Inside the basin, the floor lies far below the average lunar elevation, creating a depression ringed by highlands. The depth suggests that the impact penetrated through much of the crust, exposing lower crustal and even upper mantle materials. This makes the basin one of the best places to study lunar composition beyond the surface. Data from spacecraft instruments show that the basin floor differs from surrounding highlands. Spectroscopy reveals minerals such as pyroxene that are less common on the surface elsewhere. These minerals are typical of deeper layers, supporting the idea that the impact excavated material from beneath the anorthositic crust. Gravity mapping also shows that the crust here is thinner than average, consistent with excavation and rebound after the impact. The basin has become a focus for missions aiming to sample or observe materials from deeper within the Moon. The origin of the South Pole Aitken Basin raises important questions. Its immense size indicates a colossal impactor, perhaps tens of kilometers in diameter. The timing is less certain, but many researchers place it in the period known as the Late Heavy Bombardment around 4 billion years ago, when the inner solar system experienced a surge in large impacts. If correct, the basin is a record of that turbulent time. Its preservation across billions of years is possible because the far side did not undergo widespread volcanic flooding. On the near side, such a basin might have been filled by basalt and partly obscured, but on the far side it remains visible. Later craters dot its floor and rim, but the underlying depression still dominates. The basin also influences the distribution of elements on the Moon. Measurements show that thorium and other heat-producing elements are scarce in this region, unlike many near-side basins. This suggests that the excavation did not dredge up those materials, or that they were never abundant here. The asymmetry between hemispheres extends even into the deepest scars. From a descriptive standpoint, the South Pole Aitken Basin presents a vast and rugged terrain. Mountains along its rim rise steeply, fractured by countless smaller impacts. The floor is uneven, dotted with central peaks from later craters and coated with debris. To an observer standing within the basin, the horizon would be ringed by distant high walls, while the ground beneath would slope gently across many kilometers toward the basin's low interior. Shadows would lengthen dramatically across this landscape as the sun moved slowly overhead, and the absence of atmosphere would give every detail sharp relief. The basin's size also makes it an important landmark for navigation and mapping. Spacecraft orbiting the Moon adjust their paths as they pass over its gravity anomaly. Landers must account for its rugged topography. Missions targeting the far side often aim near or within its boundaries because the scientific return is so great. China's Chang'e 4 mission, which successfully landed in 2019, chose Von Karman crater inside the South Pole Aitken Basin. From there, instruments have studied the local geology, measured radiation levels, and tested radio observations shielded from Earth. Results confirm that the basin floor contains rocks richer in materials from deep within the Moon, although the full picture awaits returned samples. Beyond science, the basin matters for potential resources. Some permanently shadowed regions near the South Pole at the basin's edge may trap water ice. These deposits form where sunlight never reaches, and where cold temperatures preserve volatile molecules delivered by comets or produced by solar-wind interactions. While exploration of such deposits is ongoing, their presence ties the ancient impact basin to present interest in lunar resources. The basin also plays a role in ideas for astronomy. The far side is free of radio interference from Earth, and its large, stable interior offers possible sites for future radio observatories. While no such project has yet been built, the South Pole Aitken Basin remains a candidate location in many plans. Scientists continue to debate details of the basin's formation. How large was the impactor and what was its velocity? Did the collision melt large portions of the Moon's mantle, or only excavate without complete melting? What role did the basin play in the Moon's thermal evolution afterward? Each question connects to models of planetary bombardment and interior dynamics. The evidence points toward an event of extraordinary scale, but the precise consequences remain subjects of study. Regardless of the open questions, the South Pole Aitken Basin stands as a defining feature of the far side. It is a mark of violence written in stone, but in the calm present it appears as a silent depression under slow sunlight. Its mountains and valleys change only under the rare arrival of new impacts. Its floor remains still coated in fine dust. The basin does not announce its importance, yet its presence shapes the scientific understanding of the Moon more than almost any other single structure. For billions of years it has rested in place a record of one of the largest blows endured by the Moon. Each new mission adds to the picture-refining measurements of mineral content, crustal thickness, and thermal history. Yet even without instruments, the sheer size of the basin tells a story. It is a reminder that the far side holds not just small differences from the near side, but also some of the most remarkable structures in the solar system. The South Pole Aitken Basin is not hidden from the Sun, nor hidden from observation by modern spacecraft, but it is hidden from the direct view of human eyes on Earth. Its vastness remains known through careful mapping and exploration, slowly revealing how one hemisphere of the Moon carries the scars of impact in ways the other does not. One of the most important differences between the near side and the far side of the Moon lies in the distribution of heat-producing elements. These elements, especially potassium rare earth elements and phosphorus collectively called creep, play a major role in maintaining internal heat and in driving volcanic activity. On the near side, orbital spectroscopy shows that creep materials are concentrated beneath and around the large Maria basins. On the far side, these elements are scarce. This uneven distribution contributes strongly to the asymmetry between hemispheres. Creep materials are byproducts of the crystallization of the lunar magma ocean. As minerals such as plagioclase and pyroxene formed and separated out certain incompatible elements, those that do not fit easily into common crystal structures, became concentrated in the residual melt. This melt remained enriched in radioactive isotopes of potassium, thorium, and uranium. These isotopes release heat as they decay, creating localized thermal anomalies. Where creep is abundant, the crust and mantle stay warmer for longer, making volcanic eruptions more likely. On the near side, this enrichment coincided with thinner crust, allowing basaltic magma to erupt and flood the surface repeatedly. On the far side, the absence of significant creep meant that the crust cooled faster and the mantle solidified earlier, leaving little opportunity for extended volcanism. The evidence for this contrast comes from gamma-ray spectrometers on spacecraft. These instruments detect characteristic emissions from radioactive decay. Maps show that thorium and other elements cluster on the near side, especially around Oceanus Procellarum and Mare Imbrium. By contrast, the far side registers only low levels. The pattern is stark and matches the difference in volcanic history. Scientists use this distribution to model the Moon's thermal evolution. They find that the presence of creep on the near side could have sustained magmatic activity for hundreds of millions of years longer than on the far side. It also may have contributed to the formation of dense mantle materials beneath the Maria, creating gravitational anomalies called mascons. The far side, lacking such concentrations, shows fewer mascons and fewer basalt plains. The question of why creep concentrated on one hemisphere remains open. Some models suggest that in the aftermath of the Moon's formation, Earth's heat radiated toward the hemisphere facing it, slowing cooling and causing residual melts to pool there. Others proposed that large impacts stirred and redistributed material unevenly. Another idea is that convection currents within the magma ocean caused chemical segregation on a hemispheric scale. Each scenario attempts to explain how incompatible elements that should have been spread globally ended up clustered on one side. None of these models has been proven decisively, but all recognize that the asymmetry is real and fundamental. The implications extend beyond volcanism. Because creep contains thorium and uranium, it also provides a record of how radioactive heating shaped the Moon's interior. Understanding its distribution helps refine models of how long the interior remained partially molten, and how crust and mantle differentiated. It also affects calculations of how quickly the lunar core may have cooled, and whether any magnetic dynamo could have operated in the past. The far side's deficiency in creep means it serves as a baseline for a cooler, less active Moon. Comparing samples from both hemispheres could show how chemical differences influence planetary evolution. Descriptively, the presence or absence of creep is not visible to the eye, but its consequences are. Standing on the near side plains, one sees wide, dark surfaces created by repeated basaltic floods. Standing on the far side, one sees rugged highlands with only rare basaltic patches. The underlying cause of this contrast lies partly in the thermal boost provided by radioactive elements. Without them, magma does not persist near the surface. Without magma, plains do not form. Instead, the feldspathic crust endures. The far side landscape is therefore indirectly shaped by what it lacks. Another perspective comes from cratering. On the near side, many large craters are filled or partly obscured by lava flows. On the far side, where volcanism was minimal, craters remain more complete. This difference again traces back to the absence of creep enrichment. The thicker crust and lower internal heat left impacts exposed rather than buried. Thus, a geochemical detail leads to a global visual distinction. Scientists consider creep to be a tracer for the end stages of magma ocean solidification. Its concentration on the near side may mark the final stages of crystallization, when residual melts became trapped beneath thinner crust. The far side with thicker crust may have allowed less of this residual melt to pool near the surface. This interpretation fits with gravity and topographic data showing crustal differences. The story is consistent even if the exact mechanism is not yet agreed upon. From the reflective standpoint, the asymmetry raises open questions. Why does a body as small as the Moon preserve such a sharp chemical boundary between hemispheres? Did similar processes occur on other planets, but later erased by tectonics or volcanism? Could the Moon provide a unique case where early chemical segregation remains visible because subsequent activity was limited? These questions drive ongoing research. Missions that can return far-side samples, especially from regions near the South Pole Aitken Basin, would provide crucial data. By comparing isotopic compositions with near-side creep, rich basalts, scientists can determine whether the differences arise from initial formation or later redistribution. They can also refine models of how radioactive heat shaped the interior. Even now, orbital data continue to sharpen the picture. Each new map of thorium, uranium, and potassium confirms that the far side is depleted. Each new analysis of crater counts confirms that volcanism was minimal. The two lines of evidence support each other and strengthen the conclusion. The far side highlands are the product of a crust that cooled quickly and remained stable, while the near side plains are the product of a crust warmed and weakened by radioactive decay. To describe this clearly is to connect surface appearance with internal chemistry. The Moon is not uniform. Its dual face reflects both structure and composition. The far side is not hidden in mystery, but it does carry records of processes that unfolded differently beneath its crust. It is an archive of feldspathic highlands, sparse volcanism, and low creep abundance, all consequences of how elements sorted themselves in the first molten ocean. This quiet distinction explains much of what one sees when comparing hemispheres, and it remains one of the central puzzles of lunar science. Although the far side of the Moon appears almost entirely covered in bright highlands, careful analysis has revealed that it is not completely without volcanic history. Beneath the surface in certain regions lie hidden basaltic deposits known as cryptomeria. The term means hidden seas because these deposits resemble the maria on the near side but are buried beneath layers of highland material and ejecta. Their discovery shows that the far side did experience episodes of volcanism, though on a smaller scale, and often concealed by later impacts. Cryptomeria were first suspected when orbital remote sensing detected patches of dark soil that did not match the surrounding anorthositic terrain. These areas appeared to contain higher concentrations of iron and titanium elements that are common in basalt. Later, gamma-ray and neutron spectrometer data confirmed the presence of such materials beneath the regolith. The pattern suggested that lava had erupted in the distant past, filling low-lying basins, but that subsequent impacts and ejecta from neighboring craters buried them under brighter debris. The basaltic plains of the near side remained exposed while those on the far side were concealed. One of the clearest examples lies in the region of Mare Ingeni, a small patch of exposed basalt that hints at more extensive hidden flows. Surrounding this region, orbital measurements detect signals consistent with buried basalt. Other suspected cryptomeria exist in basins such as Apollo and Schiller. These regions show geophysical evidence of basaltic fill beneath a surface that appears pale and rugged. The thickness of the overlying highland debris varies, but in some cases it may reach several kilometers, enough to obscure all visual signs of lava plains. The formation of cryptomeria follows the same general process as exposed maria. After a large impact creates a basin, the crust is fractured and thinned, allowing magma to rise from the mantle. On the near side, repeated eruptions filled such basins and left broad plains. On the far side, eruptions were fewer and less voluminous. They still filled basins with basalt, but later impacts scattered highland material across them, covering the dark surfaces. Over time, micrometeorite gardening and space weathering further blended the deposits, leaving no clear trace on the surface. Only instruments that measure composition can detect them. The existence of cryptomeria carries important implications for lunar science. It shows that the far side was not completely inactive. Magmatic processes did occur, but in a more subdued form. This supports the idea that the Moon's mantle once produced magma globally, but that the ability of magma to reach the surface depended on local conditions such as crustal thickness and heat concentration. Where conditions were unfavorable, as on most of the far side eruptions, were limited and their products easily buried. The cryptomeria also help refine models of lunar chronology. By counting craters on surfaces above and around these hidden deposits, scientists can estimate when the eruptions occurred. Many cryptomeria appear to have formed during the same general period as near-side maria around 3 to 4 billion years ago. This suggests that mantle processes were active across the whole Moon at that time, even if the surface record is uneven. The difference lies not in timing but in visibility. From a descriptive perspective, Cryptomaria do not present a distinct landscape to the human eye. A traveller crossing such a region on the far side would see the same rugged highlands as elsewhere. Craters of many sizes overlap ejecta blankets spread across the surface, and no wide dark plains appear. Only subtle changes in soil composition would hint at the buried basalt. Instruments that measure reflected sunlight at specific wavelengths would detect more iron-rich minerals, but to the eye the ground remains pale. This hidden character reinforces the idea that the far side holds secrets that cannot be uncovered by simple observation. It requires detailed measurement to reveal its volcanic past. Scientists continue to search for more Cryptomaria. New missions with advanced spectrometers map the far side in greater detail, and gravity data from orbiters reveal mass anomalies that may correspond to buried basalt. Each new discovery expands the picture of how volcanism shaped the Moon unevenly. The presence of Cryptomaria also raises questions. Why were these deposits buried while near Side Maria remained exposed? Did ejecta from specific large impacts such as those that created Imbrium or Orientali spread debris far across the far side and cover earlier lavas? Did the far side experience fewer or less intense eruptions, producing thinner basalt flows that were more easily hidden? Each question leads to further study. In reflective terms, the discovery of Cryptomaria emphasizes the importance of indirect evidence in planetary science. Much of what is known about the far side comes not from direct sight, but from measurements of light particles and gravity. These tools reveal a history that the surface alone does not show. They also remind us that absence of visible features does not mean absence of processes. The far side has long been thought of as a place without seas, but beneath its highlands lie records of magma that once reached the surface. The far side's Cryptomaria are quiet, concealed witnesses to the Moon's broader volcanic era. They extend the story told by the near-side plains, confirming that magmatic activity was global, but varied in expression. They also add complexity, showing that burial and preservation play as much a role in shaping planetary surfaces as eruption itself. To recognize them is to add another layer of detail to the map of lunar history. Thus, the far side is not only a place of highlands and ancient crust, but also a place where hidden basaltic seas lie beneath the surface, waiting for instruments to detect them. These Cryptomaria expand the sense of what is preserved in the shadows, where ordinary sight reveals little, but where careful measurement uncovers a deeper story. At the poles of the Moon, especially on the far side, lie craters where sunlight never reaches. These are called permanently shadowed regions. Because the Moon's axis is tilted by only about 1.5 degrees, the Sun always hangs low above the horizon. Inside deep polar craters, the walls are high enough to block sunlight year-round. Temperatures in these places remain far below the freezing point of water, often below -150 degrees Celsius. In such extreme cold, volatile substances that would normally escape into space can become trapped for billions of years. This is how water ice and other volatiles accumulate in the shadows. The discovery of polar ice began with orbital radar studies. Some craters near the poles reflected radar signals in a way consistent with ice deposits. Later missions, such as Lunar Prospector and Lunar Reconnaissance Orbiter, confirmed elevated hydrogen concentrations in the polar regions, again pointing to the presence of water. The most direct evidence came when a spacecraft deliberately crashed into a permanently shadowed crater, and instruments detected water vapor and ice grains in the plume. These findings showed that the Moon, once thought to be bone dry, actually holds water in its coldest places. The far side contains many such shadowed regions, particularly around the South Pole, where the terrain is rugged and craters overlap. Shackleton crater, located almost exactly at the pole, has a flaw in permanent darkness. Other craters along the rim of the South Pole Aitken Basin also trap sunlight and host potential ice. Because the far side is hidden from Earth, these regions can only be studied by orbiters or landers, relaying signals through satellites. The presence of ice has several important scientific implications. First, it records the delivery of volatile material to the Moon over time. Comets, asteroids, and solar wind particles can all bring hydrogen and oxygen. In sunlight, these would be lost quickly, but in shadow they can remain. By analysing the composition of polar ices, scientists can learn about the history of volatile delivery to the inner solar system. Second, the ice helps explain processes of migration across the lunar surface. Molecules released by impacts or sputtering can hop in ballistic trajectories, bouncing across the surface until they encounter a cold trap. Over millions of years, this process leads to gradual accumulation of volatiles in shadowed craters. The distribution of ice therefore reflects not just local conditions, but also global circulation of molecules on an airless body. The deposits are not sheets of pure ice. Instead, they are mixed with regolith, perhaps as grains coated with frost, or as small patches within the soil. Their abundance is measured in weight percent, with some regions showing several percent ice by mass. This makes them significant but not immediately obvious to the eye. A human standing at the rim of a shadowed crater would see darkness below with no direct view of the ice. Only instruments sensitive to reflected light at infrared wavelengths or to neutron emissions would detect the hidden water. For potential future exploration, such ice deposits are important because they could serve as a resource. Water can be used for drinking, oxygen for breathing, or hydrogen and oxygen for fuel. While such uses lie outside the scope of calm description, they explain why these regions are of great interest. For now, the focus remains on their scientific meaning. The far side's shadowed craters are among the coldest known places in the solar system, rivaling temperatures on distant Pluto. They act as natural freezers, preserving molecules for eons. Some craters may contain layered deposits recording different episodes of delivery. If so, they are like archives of solar system history written in frost. The challenge is accessing them without disturbing the record. Missions that can scoop samples or drill carefully may one day reveal the composition in detail. For now, remote sensing continues to refine the picture. Instruments detect hydrogen concentrations, measure reflectance, and map temperatures. Each dataset adds resolution, showing where ice is most likely and how much might be present. The far side's polar shadows are part of this effort, complementing near-side studies. The contrast between daylit and shadowed ground in these regions is extreme. Just meters away from permanent shadow slopes may receive nearly constant sunlight and reach high temperatures. This sharp boundary creates unusual thermal environments, with gradients greater than almost anywhere else on the Moon. Regolith near the edges experiences repeated cycles of heating and cooling, while just inside the shadow, the ground remains locked in deep cold. This juxtaposition is a defining feature of the poles. From a descriptive standpoint, standing at the rim of Shackleton or another far-side crater at the South Pole would present a unique scene. The sun would skim the horizon, casting long shadows across nearby peaks. Looking down into the crater, one would see only darkness, a pit never touched by sunlight. Instruments aimed into the shadow would record temperatures close to absolute zero, yet the surface dust and possible ice grains would remain silent and still. No glimmer would betray their presence to the unaided eye. The recognition that such dark craters contain water has reshaped the scientific understanding of the Moon. Once regarded as a dry, lifeless rock, the Moon is now known to harbour hidden reservoirs of volatiles. The far side contributes to this picture by hosting some of the largest and most stable cold traps. These places remind us that even in the most barren landscapes, small pockets of complexity endure. The processes are mechanical and chemical, not dramatic, but their persistence across billions of years gives them weight. The story of polar shadows is not one of hidden seas, but of hidden grains preserved by geometry and cold. The moon's minimal axial tilt ensures that certain craters never see the sun. The absence of atmosphere prevents heat from circulating. The result is a set of natural vaults where water delivered from beyond can remain frozen in place. In the slow rhythm of lunar time, these deposits accumulate and wait. To describe them is to acknowledge that the far side holds not only ancient crust and impact scars, but also quiet reservoirs of ice stored in perpetual night. One of the most unusual qualities of the far side of the moon is its natural silence in radio frequencies. Because the moon is tidally locked, the far side never faces Earth. Earth itself is a powerful source of radio emissions, both natural and artificial. Lightning storms, auroral processes, and above all human technology produce continuous radio noise. On the near side of the moon, these signals reach the surface unimpeded. On the far side, the bulk of the moon blocks them completely. The result is a shielded zone free from terrestrial interference. This unique environment has been recognized since the earliest days of radio astronomy as an ideal place to study the universe at very low frequencies. Radio waves longer than 10 meters cannot penetrate Earth's ionosphere, which means they never reach ground-based detectors. Only in space above the ionosphere can these long wavelengths be observed. Even then, spacecraft in Earth orbit are exposed to the constant chatter of human transmissions. The far side of the moon offers something different, a large stable platform permanently sheltered from that interference. From a descriptive standpoint, the surface itself does not look different because of this property. A person standing on the far side would not see any sign of the radio quiet zone. The landscape remains the same rugged highlands and craters. This silence is electromagnetic rather than acoustic. To an instrument tuned to long wavelengths, however, the difference would be profound. Where on Earth the spectrum is crowded with overlapping signals, on the far side the spectrum is empty and clean. This makes the far side a natural observatory for phenomena that are otherwise hidden. Scientists imagine placing radio antennas across the floor of large craters, where they could listen to the cosmos in a range of frequencies never before explored in detail. Such instruments could detect the faint hiss of hydrogen from the cosmic dark ages, the time before the first stars formed. They could trace low-frequency emissions from planets around other stars, or study the activity of our own sun without interference. The potential is vast, and it depends entirely on the quiet created by the moon's shielding. Missions have already tested this idea. Small satellites orbiting the moon have carried antennas to measure the radio environment. They confirm that the far side is indeed shielded from Earth signals. Only when the spacecraft move around the limb and Earth comes into view does the noise return. On the far side, the instruments record a still background limited only by natural cosmic sources. This verification strengthens the case for future observatories. The far side's shielding is not perfect at all times. When the moon is between Earth and the sun, Earth's radio emissions are blocked, but solar radio bursts may still reach the far side. When the moon is elsewhere in its orbit, galactic and solar sources remain visible. The key point is that human-made interference, which overwhelms many frequency bands, does not reach the far side at all. For scientists seeking to detect extremely faint cosmic signals, this difference is decisive. The far side is not just quiet, it is the quietest natural location available in the inner solar system. From a reflective standpoint, this quality highlights how the same tidal locking that keeps one hemisphere always facing Earth also creates an environment shielded from Earth's influence. What seems like a simple orbital arrangement produces a unique scientific opportunity. The Moon serves as a barrier, its bulk absorbing or deflecting radio waves, leaving a zone of clarity behind it. This geometry cannot be reproduced anywhere else near Earth. Even at great distances in space, spacecraft remain within reach of transmissions leaking from Earth. Only the lunar far side provides permanent shelter. The vision of a radio observatory on the far side often centers on specific sites. One idea is to place antennas inside large, deep craters where terrain itself offers further protection. The floor of the South Pole Aitken Basin, already a focus of geological interest, is also a candidate site. Its size could accommodate wide arrays of simple wire antennas spread across regolith and connected by relay satellites in lunar orbit. Another concept imagines small landers, each deploying antennas forming a network that listens together. The simplicity of such antennas makes them attractive for long-term missions. Their effectiveness depends not on complexity, but on the absence of interference which the far side provides naturally. The importance of this environment is emphasized by comparison. On Earth, even in remote deserts or polar regions, radio telescopes must contend with interference from satellites, aircraft, and distant transmitters. Filters and data processing can remove some noise, but the stronger signals remain overwhelming. On the far side, no such mitigation is necessary. The spectrum is clean from the outset. To scientists accustomed to crowded data, this is transformative. From a descriptive angle, the concept of a quiet radio sky is hard to convey without instruments. The ground remains silent either way, and human ears hear nothing. Yet the absence of interference can be imagined as an emptiness in an otherwise noisy band. The Moon's far side is like a deep cave in which outside sounds cannot enter, except that the sounds in question are radio emissions. Within that cave, the faintest whispers of cosmic history can be heard. Beyond the scientific benefits, the recognition of the far side as a radio quiet zone has led to discussions about preservation. International agreements have been proposed to designate it as a protected area for radio astronomy, limiting future human activities that might generate interference. These discussions are ongoing, but they reflect how unique the environment is. There is no replacement if the quiet is lost. Thus the far side is valued not only for its geology, but also for its electromagnetic silence. The link between the two is geometry. Tidal locking ensures that one face always points away from Earth. That orientation both hides the landscape from earthly eyes and shelters it from earthly signals. The result is a hemisphere defined as much by what it does not receive as by what it contains. It is not darker than the near side, but it is quieter in radio terms. This quality, though invisible and intangible to ordinary senses, has become one of the most significant aspects of the far side in modern science. It promises insights into cosmic history and planetary magnetospheres, into the behavior of stars and the structure of the universe, all because a silent zone exists behind a locked orbit. In this way, the far side reminds us that absence can be as important as presence. The absence of radio noise is a resource just as much as the presence of highland crust or polar ice. It is another hidden aspect of the Moon revealed not by sight, but by careful listening with the right instruments. The far side of the Moon holds another class of features that remain both intriguing and uncertain. These are localized regions of crustal magnetism and associated surface markings called lunar swirls. Unlike Earth, the Moon no longer has a global magnetic field. Its core does not generate a present-day dynamo. Yet orbiting spacecraft have detected patches of magnetic field preserved in the crust. Some of these magnetic anomalies are strong enough to deflect portions of the solar wind. Where this happens, the surface develops unusual bright markings. These curving high-contrast patterns are called swirls. They appear in several places, but one of the most striking examples lies in Mare Ingeni on the far side. To the eye, a swirl looks like a bright, sinuous streak across the darker or lighter ground. It winds in irregular loops and bands, sometimes stretching for tens of kilometers. Unlike impact craters or volcanic features, swirls have no raised rims or depressions. They do not correspond to topographic changes. Instead, they are purely surface markings. Their brightness results from differences in how the soil has been weathered. On the Moon, solar wind particles gradually darken and redden the regolith by implanting hydrogen and altering tiny grains of iron. In regions where local magnetic fields deflect the solar wind, this weathering is reduced. The soil stays brighter and less reddened. The result is a swirl pattern that marks the boundary between shielded and unshielded regions. The existence of crustal magnetic fields raises questions about the Moon's past. One possibility is that the Moon once had a global magnetic field generated by a molten convecting core. If so, crustal rocks could have been magnetized while still hot. Later, as the dynamo shut down, those remnant fields remained frozen in the crust. Another possibility is that large impacts generated short-lived magnetic fields by stirring molten material and driving electrical currents. These impact-induced fields could have magnetized nearby crust. Either way, the anomalies are patchy rather than global, and their strengths vary. Some are associated with large basins, while others appear more isolated. The swirls themselves do not always align with the strongest anomalies, adding complexity to the story. For Mare Ingini, the swirl pattern overlaps with a region of strong crustal magnetism. The markings are bright and sinuous, crossing the surface without regard to craters or ridges. In images, they appear almost painted, on a striking contrast against the ancient highlands around them. To stand within one would be to see the ground brighter than in surrounding areas, though the difference is subtle to the human eye. Instruments, however, record clear changes in reflectance and in spectral properties. Scientists continue to study these features with orbiters carrying magnetometers and cameras. They map the fields, measure particle fluxes, and compare soil properties. Models suggest that swirls form where miniature magnetic shields reduce the solar wind flux. Yet the details remain debated. How strong must the field be, and how long must it last to maintain such markings across millions of years? Could the swirls be partly due to electrostatic transport of dust, driven by interactions between charged grains and local fields? These questions keep the subject open. From a broader perspective, the existence of magnetic anomalies on the Moon ties into larger questions about planetary magnetism. Many bodies once had dynamos that later ceased. Studying the Moon helps explain how long such dynamos can persist in small bodies and what processes sustain them. Rock samples that show remanent magnetization support the idea that a lunar dynamo once operated for several 100 million years. If true, the crustal anomalies are fossil records of that era. On the far side, the combination of magnetism and swirls makes for landscapes that are both geologically ancient and surprisingly dynamic in appearance. While most of the highlands are uniformly cratered and weathered, the swirls cut across them like fresh brush strokes. They are reminders that even in a place dominated by impacts and frozen crust, subtle interactions between the sun and local fields can create ongoing patterns. From a descriptive standpoint, the swirls stand out against the stark terrain. Imagine walking across a plain of pale dust, then suddenly entering a zone where the ground appears brighter, looping in graceful arcs. There are no ridges or troughs, no boulders to mark a boundary, only a change in reflectance that follows invisible magnetic lines. Above, the black sky shows the sun casting direct light, yet the ground seems to have painted patterns independent of topography. The impression is both subtle and striking. The mystery of their formation invites continued exploration. Instruments flown on orbiters, and perhaps in the future deployed on landers or rovers, can measure soil chemistry and magnetic properties directly. Each new dataset refines the picture. Scientists hope to determine whether swirls can persist for billions of years or whether they require ongoing processes to remain visible. If they are ancient, they are relics of a time when the moon held a stronger magnetic environment. If they are recent or maintained, they demonstrate that small-scale interactions between crust fields and the solar wind can still shape the surface. Either outcome is valuable. The far side contributes to this story by hosting some of the most distinct examples, such as Marangini. In addition, other anomalies exist near basins like Crisium and Serenitatis on the near side, but the distribution is uneven. The fact that they occur on both hemispheres suggests a global process, whether a dynamo or impacts, but the far side provides crucial case studies. In reflective terms, the swirls remind us that not all lunar features are straightforward. Craters and basins can be explained by impacts, maria by volcanism, highlands by crustal flotation. Swirls defy such simple categories. They are surface markings created not by topography, but by the interplay of fields and particles. They're hidden in plain sight, detectable by their brightness, but dependent on invisible forces. Their presence on the far side underscores the variety of hidden stories written across the moon. They add another layer to the narrative, showing that even in a world dominated by ancient events, subtle and ongoing interactions continue to mark the ground. The far side is not simply a static archive of the past. It also hosts features shaped by present solar wind and magnetic interactions. To recognize this is to expand the sense of what is hidden there, not only crustal composition and buried basalts, but also magnetic brushstrokes that bend and loop across the surface. These patterns are quiet, enduring, and enigmatic, inviting patient study, rather than dramatic interpretation. The surface of the far side, like the near side, is covered by a layer of loose material called regolith. This layer is not soil in the earthly sense because it does not form from biological processes or weathering by air and water. Instead, it is produced entirely by bombardment and radiation. For billions of years, micrometeorites have struck the moon, each impact breaking rocks into smaller fragments and scattering debris. Solar wind particles implant themselves into the upper grains, altering their chemistry. Temperature extremes cause thermal cycling that fractures rocks further. The result is a surface blanket of fine dust and crushed rock that may be several meters thick in places. The regolith on the far side develops more slowly than one might expect, but its processes are steady and unending. Each micrometeorite, traveling at tens of kilometers per second, strikes with enough energy to shatter minerals and melt small amounts of rock. These impacts create tiny glass spherules that mix with dust and crystalline fragments. Over time, repeated strikes churn the surface, a process called gardening. Gardening mixes older and younger material, buries some particles, and exposes others. The continual mixing means that a single handful of regolith may contain grains of many different ages, some billions of years old, and others created recently. Solar wind implantation adds another layer of complexity. Hydrogen and helium nuclei from the sun penetrate the upper nanometers of grains, leaving chemical traces. When later impacts melt or vaporize those grains, the implanted atoms are released, providing information about past solar activity. By studying regolith, scientists can therefore learn not only about the moon, but also about the history of the sun. On the far side, where Earth's magnetosphere rarely shields the surface, the implantation record may be clearer. Thermal cycling adds further alteration. With no atmosphere, surface rocks face direct sunlight during the long lunar day, heating to over 100 degrees Celsius, and then plunge into deep cold during the 2-week night. This repeated expansion and contraction gradually weakens and fractures rocks. Pieces break away, joining the regolith. Dust grains continue to be ground smaller by impacts, creating a surface that is both powdery and sharp-edged. From a descriptive standpoint, the regolith is grey, fine and clingy. Astronauts on the near side described it as clinging to suits and abrasive to equipment. On the far side, it would be similar, though its exact chemistry varies depending on local geology. In highland regions dominated by anorthosite, the regolith contains more feldspar fragments. In basaltic patches, it contains more pyroxene and olivine. The regolith reflects the underlying rock mixed and altered by billions of years of bombardment. Another key aspect is the depth of the regolith. In heavily cratered highlands, the layer may be thicker because of the constant supply of ejecta from impacts. In younger basalt plains, it may be thinner. The far side, being dominated by old highlands, tends to have thicker regolith overall. This makes it a particularly rich archive of past processes, though it also presents challenges for landing and mobility. Spacecraft that touch down must account for the softness and dustiness of the surface. Scientific interest in regolith goes beyond its composition. It records the frequency and size distribution of impacts over time. Each crater scatters ejecta that mixes into the surface. By examining grain sizes, glass content, and maturity indicators such as the presence of agglutinates, grains welded together by micrometeorite impacts, researchers can reconstruct the impact environment. The far side's regolith, less disturbed by resurfacing lava flows, provides a longer and more continuous record than the near side. In addition, the regolith may hold tiny fragments from beyond the Moon. Some meteorites that strike Earth also strike the Moon. Traces of asteroidal or even terrestrial material may be preserved in the lunar soil. Studies of Apollo samples have found tiny grains that may be remnants of early Earth rocks blasted into space by impacts and deposited on the Moon. On the far side, similar processes could have delivered exotic grains, though none have yet been directly sampled. Future missions may reveal whether the far side regolith contains such records. From a reflective standpoint, the regolith shows how even without atmosphere, water or biology, a planetary surface is never static. The Moon appears still, but its skin is constantly being reshaped at a slow pace. Each micrometeorite strike is a tiny event, yet their cumulative effect is profound. The ground is churned, melted, fractured, and implanted with atoms over and over. The far side has experienced this process just as much as the near side, perhaps even more clearly, because it has not been resurfaced by lava in most places. For an observer standing on the far side, the regolith would feel soft underfoot, yet resistant with fine grains that scatter in low gravity. The dust would rise easily when disturbed, hanging briefly before settling back in slow motion. The surface would stretch outward as a patchwork of cratered ground all coated with the same grey blanket of dust. Every step would stir material that has been shaped by billions of years of cosmic events. The regolith also influences temperature and reflectivity. Because it is porous and insulating, it allows surface temperatures to fluctuate more strongly. Daytime heat penetrates only a few centimeters before being stored or re-radiated. Nighttime cold sinks quickly. Instruments placed on the surface measure steep gradients. These thermal properties matter for landers and instruments, but they also illustrate how the upper skin of the Moon behaves differently from solid rock. The regolith is a dynamic interface between space and interior. In scientific terms, it is both an obstacle and a resource. It complicates landings, clings to equipment, and obscures fresh bedrock. Yet it also stores a record of impact solar wind and interplanetary material. On the far side, it provides perhaps the clearest archive of the Moon's history, because the absence of widespread maria leaves more ancient regolith undisturbed. For researchers, this means that samples from the far side are especially valuable. They would allow cross-comparison with Apollo samples and fill gaps in the record. Missions that can return regolith from the far side, particularly from the South Pole Aitken Basin, or from polar shadowed regions could yield insights into both lunar evolution and solar system history. From a calm descriptive view, the regolith is simply dust and rock fragments lying silent under the sun. Yet within its grains lie clues to billions of years of events, written not in words but in textures, isotopes and chemistry. The Farside's regolith, churned by micrometeorites implanted by solar wind and fractured by temperature swings, is as much a hidden archive as any crater or basin. To study it is to read the moon's slow diary, kept not by intent, but by steady natural processes acting across deep time. To understand the far side of the moon in detail, scientists rely heavily on gravity mapping. Gravity is not uniform across the lunar surface. Variations in crust thickness, buried structures, and concentrations of dense rock create local differences. These variations are called gravity anomalies. By measuring how spacecraft accelerate or decelerate as they orbit, scientists can map these anomalies and infer what lies beneath the surface. One of the most ambitious efforts in this field was the Gravity Recovery and Interior Laboratory mission known as GRAIL. It launched in 2011 and placed 2 spacecraft in tandem orbit around the Moon. By measuring the distance between them with extreme precision, scientists could detect minute changes in gravity. As one spacecraft passed over a region of slightly stronger gravity, it sped up slightly, changing its separation from the other. These tiny shifts, measured down to microns, were combined to create the most detailed gravity map of the Moon ever produced. The results transformed the understanding of the far side. The maps showed that the crust on the far side is significantly thicker than on the near side, confirming earlier suspicions. In many regions it reaches 70 kilometers, while on the near side it averages closer to 30 or 40 kilometers. This thickness explains why volcanic eruptions are rare on the far side, since magma has more difficulty breaking through. Gravity data also revealed details of large impact basins. On the near side, many basins contain mass concentrations or mascons. These are regions where dense mantle material has risen, or where basalt fills the basin, creating a gravity high. Spacecraft orbiting over mascons are pulled downward, slightly altering their paths. On the far side, however, mascons are fewer and less pronounced. Many basins show no evidence of dense infill. Instead, they retain thicker crust and less volcanic flooding. This distinction is another confirmation of hemispheric asymmetry. The South Pole Aitken Basin provides a clear example. Gravity data there show a thin crust and expose deeper materials consistent with excavation by a massive impact. Yet the basin does not contain the same kind of mascon seen in near-side basins like Imbrium. This suggests that the far-side impact basins did not fill with large volumes of basalt. The difference reflects both crustal thickness and the distribution of heat-producing elements. Gravity mapping also reveals structures beneath the surface that are invisible in photographs. Linear features called dikes created by ancient intrusions of magma sometimes show up as elongated anomalies. Buried basin rings obscured by later impacts can be traced by circular patterns in the gravity data. These subsurface structures provide evidence for events that shaped the far side billions of years ago. Another important result from gravity mapping is the insight into the Moon's internal layering. By modelling the gravity field, scientists can estimate the density of the crust mantle and core. The far side's thicker crust means that its density distribution differs from the near side. This helps explain the overall shape of the Moon, which is slightly elongated along the Earth-facing axis. It also constrains theories about how the Moon cooled and differentiated after its formation. Gravity anomalies provide not only scientific information but also practical guidance. Spacecraft navigation requires precise knowledge of gravitational variations to maintain stable orbits. Before the era of detailed gravity maps, many lunar orbiters experienced unexpected drifts and crashes because mascons perturbed their paths. With modern maps, missions can plan stable trajectories, including those that orbit low over the far side where ground communication is difficult. From a descriptive perspective, gravity anomalies are intangible. An observer standing on the surface would not feel heavier or lighter in any obvious way. The differences are measured in fractions of a percent, detectable only by sensitive instruments. Yet beneath the ground, these differences reflect real structures, a thick slab of crust, a buried mass of basalt, or a deep excavation from an ancient impact. The surface may appear the same, but the hidden mass below is not uniform. The far side's gravity field also holds clues to its early orbital history. Some scientists propose that tidal interactions with Earth may have influenced how the Moon's crust solidified and how mass was distributed. The thicker far side crust may reflect cooling under different thermal conditions, while the near side retained more residual heat and developed dense volcanic provinces. Gravity data support this by showing correlations between crustal thickness and chemical enrichment. From a reflective standpoint, gravity mapping shows how unseen forces can be charted with precision. No eye can detect a mascon, yet spacecraft reveal its presence through the faintest changes in acceleration. The far side becomes visible in a new way, not in light but in mass. This approach connects the lunar surface to deeper processes, making it possible to study layers that will never be sampled directly. The maps produced by Grail and similar missions are now essential references. They guide the interpretation of every other dataset from topography to magnetism. They remind us that the far side, though hidden from Earth's view, is not beyond reach of measurement. The quiet pull of gravity recorded in spacecraft paths opens a window into its structure. To summarize in plain terms, gravity mapping confirms that the far side crust is thicker, that its basins are less filled with dense lava, and that its anomalies differ from those of the near side. It adds depth to the picture painted by surface observations. The far side is not only a place of rugged highlands, but also a place with a distinctive interior. It is thicker, lighter in volcanic infill, and shaped by impacts that excavated without erasing their scars with basalt. These qualities are not visible to the eye, but become clear in the measurements of orbiters. For a patient observer, the lesson is that much of what is hidden in the far side lies beneath the surface, in structures recorded not by light but by gravity. The Moon's invisible pull mapped carefully reveals the architecture of its hidden hemisphere. The far side of the Moon, long hidden from direct human view, has gradually been revealed through a sequence of orbital surveys, flybys, and lander missions. Each step has added clarity, turning what was once a mysterious blank into a detailed geological map. The earliest images came from the Soviet Luna 3 spacecraft in 1959. Its grainy photographs transmitted by film developed on board and scanned line by line were the first glimpse of the far side. They immediately showed how different it was from the near side, dominated not by wide dark maria, but by bright rugged highlands. Though crude by modern standards, these images set the stage for systematic exploration. In the 1960s, both the United States and the Soviet Union sent orbiters that captured more detailed views. Lunar orbiter missions by the United States mapped potential landing sites for Apollo, but also photographed the far side extensively. The Soviet Zond probes contributed additional coverage. By the end of that decade, the general layout of far-side basins, craters, and highlands was known, though not in fine detail. Apollo astronauts never visited the far side because constant radio contact with Earth was required. However, their spacecraft did orbit around it, giving astronauts direct views and carrying instruments that collected data. Seismometers placed on the near side also detected impacts on the far side, providing indirect information about its structure. The absence of direct sampling limited knowledge, but orbital measurements grew steadily more refined. With the arrival of modern spacecraft in the 1990s and 2000s, mapping advanced dramatically. The Clementine mission in 1994 used multispectral imaging to determine surface composition. It confirmed the feldspathic nature of the far-side highlands and mapped differences in mineralogy across basins. The Lunar Prospector in 1998 carried neutron and gamma-ray spectrometers, producing global maps of elements such as iron, titanium, and thorium. These confirmed the strong contrast between near and far sides, with thorium and other heat-producing elements concentrated mainly on the near side. These results deepened the understanding of hemispheric asymmetry. More recently, missions such as Japan's Kaguya, also called Selene in 2007, China's Chang'e series, India's Chandrayaan orbiters, and the United States Lunar Reconnaissance Orbiter have produced unprecedented maps of topography, gravity, and mineralogy. Kaguya used laser altimetry to generate detailed elevation models showing the immense depth of the South Pole Aitken Basin and the ruggedness of surrounding highlands. The Lunar Reconnaissance Orbiter continues to return high-resolution images that show the far-side surface in detail down to meters. Gravity mapping from the Grail mission added the subsurface perspective, revealing crustal thickness variations. Among these, the Chang'e 4 mission in 2019 marked a new stage. It was the first spacecraft to land on the far side, touching down in Von Karman crater, inside the South Pole Aitken Basin. Because direct communication with Earth is impossible from the far side, the mission relied on a relay satellite placed in orbit around the Earth-Moon Lagrange point beyond the Moon. With this support, the lander deployed instruments and a small rover called Yutu-2. The mission measured radiation levels, studied soil properties, and observed the composition of local rocks. It also carried a small radio experiment to test the far side's shielded environment for astronomy. Results included detection of rocks rich in minerals that may have originated in the lunar mantle, confirming the basin's excavation depth. These discoveries were possible only by landing and directly measuring the terrain. Each mission builds a fuller picture. Orbital spectrometers show widespread feldspar in the crust. Neutron detectors show hydrogen concentrations near the poles. Gravity data show thickness and buried structures. Landers provide ground truth, confirming or refining orbital interpretations. Together they reveal a far side that is not a hidden mystery, but a knowable hemisphere rich in detail. The continuity of exploration also shows how different nations contribute pieces of the puzzle. The Soviet Union revealed the far side first. The United States expanded the map. Japan and India added modern data. China placed the first lander, and international cooperation continues in analyzing the results. The far side is thus a shared subject of science. From a descriptive standpoint, spacecraft imagery of the far side conveys its ruggedness vividly. High-resolution photos show countless craters overlapping ridges, extending for hundreds of kilometers, and basin floors scarred by secondary impacts. Shadows stretch long in the low sun angles of polar regions, while crater walls gleam bright under direct light. Unlike the near side, where broad, smooth plains provide visual relief, the far side appears consistently rough. The human eye, if looking out a spacecraft window, would see a landscape of pale highlands without the familiar patterns of Maria. To describe this landscape in plain terms, it is pitted bright and complex. Each new orbital pass shows details down to boulders and fractures. Each lander image confirms the regolith's grey dust and scattered rock fragments. These scenes ground the scientific measurements in visible reality. They also remind us that while the far side is hidden from Earth, it is not fundamentally different in its materials or processes. Cratering volcanism and space weathering occur on both hemispheres. What differs is the balance of these processes governed by crustal thickness, internal heat, and element distribution. The far side's exploration also provides context for broader planetary science. The Moon is the only place beyond Earth where samples have been returned and linked directly to orbital maps. This makes it a calibration point for interpreting other planetary surfaces. By studying the far side, scientists refine methods that can be applied to Mercury, Mars, and beyond. The far side is thus both a destination and a laboratory for techniques. From a reflective standpoint, the unfolding of exploration shows how hidden regions become known step by step. The far side was once a blank, a place literally unseen. Now it is mapped, measured, and even walked upon remotely by robotic wheels. Yet the pace of discovery remains deliberate. Each mission reveals new complexities from buried basalts to crustal magnetism. The far side has moved from mystery to study, but it retains challenges and unanswered questions. Samples have not yet been returned to Earth from this hemisphere. Such samples would allow direct dating of far side surfaces, testing whether its basins are older or younger than those on the near side. They would confirm mineral compositions detected remotely. Until such missions occur, orbital and lander data remain the primary sources. Still, the cumulative knowledge is vast. The far side is no longer simply hidden. It is a hemisphere with known structure, composition, and history. The story of its revelation is part of the larger story of space exploration itself, a process of patient mapping, measurement, and confirmation. It continues with each new mission, slowly filling in the details of a world once invisible. 15. As exploration of the far side of the Moon has advanced, attention has increasingly turned toward its highlands as a place of enduring stillness and quiet study. The highlands represent the original crust formed from the solidification of the lunar magma ocean more than 4 billion years ago. Because the far side has so little volcanic resurfacing, these rocks remain more intact than anywhere else. They preserve the earliest record of lunar differentiation, impact bombardment, and surface weathering. A slow walk across these highlands, if it were possible, would present a sequence of ridges, valleys, and overlapping craters, all softened by the endless blanket of regolith. The ground would be pale under the sun, brighter than the basalt plains of the near side, and sharply shadowed in the low-angle light that characterizes the long lunar day. Every feature would tell a story of impacts that span the entire history of the solar system, because nothing has erased them. The stillness of the far side highlands is not only visual but also geological. For billions of years there has been no volcanism of scale, no tectonic motion, no atmosphere to erode surfaces with wind or water. The only changes are impacts micrometeorite bombardment and radiation. Even these act slowly in human terms. Craters that formed billions of years ago remain visible. The dust that coats them has taken eons to develop. To scientists, this unchanging character is invaluable. It allows the far side to serve as a reference surface for dating other bodies. By counting craters of different sizes and comparing them with the radiometric ages from samples, researchers calibrate the chronology of planetary surfaces across the solar system. The far side provides the most complete set of cratering records since it has not been smoothed over by Maria. Each crater, each layer of ejecta, each patch of regolith contributes to a slow clock that ticks on geologic time. Instruments on orbiters show that the highlands are not uniform. Compositional maps reveal variations in feldspar content, pyroxene traces, and the effects of ejecta from large basins. Topographic maps show subtle rises and basins, evidence of ancient structures, partly obscured by later craters. Yet the overall impression remains consistent, rugged, bright, and old. The far side highlands are a single vast archive. They are also silent. Standing in such a place, one would hear nothing. The thin dust absorbs steps and no air carries sound. Shadows stretch long in the slow sunrise, then shorten at midday, then stretch again toward dusk. Stars remain visible in the black sky even at noon, and Earth never rises above the horizon. The sun alone marks the passage of time. This silence extends to the electromagnetic domain. The far side is shielded from radio noise, making it not only visually quiet, but also radio quiet. Instruments placed here measure only the faint natural emissions of space. This combination of geological stillness and electromagnetic quiet makes the far side highlands unique in the solar system. From a scientific perspective, these qualities make the highlands a prime target for future sampling. Rocks collected here would date the earliest crust test models of magma ocean crystallization and record the oldest impacts. Regolith samples would contain billions of years of solar wind particles implanted in grains, providing a history of the Sun's activity. Some grains may even contain fragments of asteroids or comets that struck long ago. Every scoop of soil is a layered archive. Missions to collect such samples must overcome the challenge of communication. Because Earth never rises, landers require relay satellites to transmit data. The Chang'e 4 mission demonstrated how this can be done. Future sample return missions are being planned with similar support. These will complete the story that Apollo began but could not finish. The far side highlands will then provide the missing half of the Moon's geologic record. From a reflective standpoint, the highlands encourage patience. They change so slowly that they embody geologic time itself. Where Earth's landscapes transform quickly under weather and life, the lunar far side endures with little alteration. This endurance makes it a stable reference for studying planetary processes. It also means that exploration must proceed carefully, so as not to disturb the very record that makes the highlands valuable. Instruments must be placed with awareness of the soil's fragility. Sampling must account for the mixing of grains by micrometeorite gardening. Navigation must consider the thick regolith that softens terrain. Each step requires slow thought. In the end, what the far side highlands offer is not spectacle but continuity. They remind scientists that the Moon is a body where ancient processes are preserved. They show how crust crystallized from a molten ocean, how impacts accumulated without erasure, how solar wind particles implanted themselves in grains, and how silence can endure in both sound and radio waves. These qualities make them a fitting conclusion to the narrative of what is hidden on the far side. Not hidden in darkness, not hidden in mystery, but hidden in plain view, until careful exploration revealed their nature. Today the far side highlands are mapped, measured, and partly explored. Yet they remain as still as they have always been. Their ridges rise under the sun, their craters lie in shadow. Their dust records each micrometeorite strike. Nothing disturbs them except the occasional new crater. They are a place where time itself seems to stretch, not because it moves differently, but because so little interrupts its flow. To walk across them would be to walk across billions of years of unbroken history, layer upon layer of stone and dust quietly holding the record of the Moon's earliest days.